Hi everyone, Christian Aparicio here to give you another lecture on optimization with MSC Nastran. Today we are going to be talking about machine learning as it relates to Nastran. Here's a quick overview of what I'm going to cover in this presentation. I don't want to make this presentation a whole day, so I'm going to be giving you an idea of what specifically in machine learning we're going to talk about. There are various types of learning algorithms and regression models that we can pick, but here I'll just give you an idea of which ones we're focusing on. I have two goals for you. The first goal is that you have an idea of how to fit a model. If you're familiar with regression modeling, say with the least squares, basically this is an extension of that, but we're using something a little different. This model, if you will, would be used to predict the output of your finite element program instead of having to run the finite element program at specific points. I'll get to this in a moment. After we go over how to fit a model, we go over acquisition functions. So your machine learning algorithm is going to have to pick the next, say, configuration of your finite element model. You're going to have to know how to choose the next point. So this is where we have a discussion on acquisition functions. That's the second goal. And then at the very end, I'll end with the conclusion and the frequently asked questions. So if you look at machine learning, there are a lot of learning algorithms, if you will. Anything from supervised all the way down to, say, robot learning. Here we're going to be focusing on the supervised learning branch. Specifically, we're going to be talking about active learning, sometimes called sequential learning. And we're going to be talking about Bayesian optimization, which helps us develop our acquisition functions later on. So this, in terms of algorithms, we're going to be focusing on active learning. Now, in terms of models, the models, remember, are used to predict the outputs of your finite element program. Here, there are a lot of different models available, but here we're going to be focusing on just the Gaussian process regression method of generating your model. Now, quick acknowledgement. Most of this presentation is sourced from this book, Surrogates, Gaussian Process Modeling, Design and Optimization for the Applied Sciences. This was written by Dr. Gramercy here. This is an excellent book, in my opinion, for anyone who's new, coming from an engineering background. This book does a great job of illustrating the fundamentals of everything I'm talking about in this presentation, and it gives you code so you can, if you wanted to do this by hand, the author gives you code so you can confirm that you're doing you have the process well understood. So that's why I like it. The code can validate the hand calculations. Fortunately, at the time of making this presentation, so today is February 26, 2020, there is actually a free ebook available at the link here. And of course, if you want to purchase a physical copy, you can also go ahead and do that. I actually downloaded the ebook first, and I found the ebook really good, so then I purchased a physical copy, and now it's in my library as a good resource. Now, let's go over the two goals we want to cover. The first goal is we want to construct our model. Here I'll be using surrogate model to differentiate from the finite element model. This surrogate model is going to be used to predict the output of MSC Nastran. Now, the methods here don't necessarily apply to MSC Nastran. They could be used for any other finite element solver. You could actually apply this to any other computer code in engineering, whether it's a computation of fluid dynamics or CFD, or it's multi-body dynamics with MBD. So now, number one, the first goal is to learn how to fit and construct your surrogate model. The second goal is to help construct the acquisition functions. The acquisition functions help you pick the next candidate point of your finite element model. Ultimately, when you have a firm understanding of 1 and 2, making sense of the final machine learning algorithm is pretty straightforward. Basically, you start off with training data. This training data is used to construct your model or your surrogate model. Your surrogate model is used to construct acquisition functions. These acquisition functions are used to yield the next candidate design. Once you have this candidate design, you then run your FE solver. Here we're using Nastran. Your output of the Nastran run validates whether or not you've found a better design, and then you repeat the process. You update your model, acquisition function, new point, run Nastran, and you go in this loop again and again until you want to stop it. So this is what ultimately we want to do. Fit the model, pick the next point via the acquisition function. So in the next few slides, we're going to be seeing a lot of exotic terminology and labels. Here, when I'm referring to X, know that these are the X inputs. So for example, if I was dealing with a 3-bar truss, each X corresponds to a different variable or parameter in your finite element model. Here, for this example, my X parameters are corresponding to the cross-sectional areas of the parameters. And now as for the Y corresponds to the outputs of your MSC Nastran run. Your outputs could correspond to many responses. They can correspond to your weights, or here you will only have one weight. They can correspond to your stresses, displacements, or any other response that you're used to outputting from MSC Nastran. So again, X corresponds to the parameters and Y corresponds to the outputs. So the first goal is fitting the model. Here we are using the Gaussian process regression method to yield our surrogate model. This surrogate model can be used to predict the output of Nastran at different points that you pick. So what's the process for this? So number one, you obtain your training data. So if we go back to the 3-bar truss example a few slides ago, we're going to take that finite element model and we are going to run it at different configurations for the cross-sectional areas. At each configuration, we're going to collect the outputs. We're going to collect the weights. We're going to collect the axial stresses, displacements, and any other response that we want to predict later on. So here, the X is every different configuration of your inputs or FE model, and then your Y is going to correspond to all of your output responses, the weight, stresses, and so on and so on. We're going to also use what's called a kernel function. Sometimes this is referred to as a covariance function. Remember, or rather, we're going to hear kernel used in various other contexts. Here, know that we're talking about something that's called a kernel function. This is not to be confused with something else, like if you're on Linux. In Linux, you talk about a kernel. That's something completely different. Here, we're talking about the kernel function or the covariance function. Once we have the training data, once we have the kernel function, we'll go ahead and use these so-called multivariate normal conditioning equations to produce what's called the mean function here on the far right and the variance function. The mean function is basically our surrogate model. This is what's going to be used to produce our predicted values. The variance is used to gauge the prediction uncertainty. If the variance is really high, the prediction uncertainty is really high. Sometimes, or rather, the MVN conditioning equations go by many names. Sometimes you'll hear these equations referred to as the Kriging equations. These are both the same. Here on this slide is just some more explanation of what all of these terms mean. For example, the covariance matrix is actually composed of 4 separate covariance matrices. For example, this first covariance matrix, if you will, this is a covariance matrix between the prediction points and itself, the prediction points. I'll go into this with actually example in a moment. So here are the first example. This is what we want to do. Suppose that we want to perform a regression of this black box function. Nastran could be seen as a black box function. We don't know what the actual function is. All we can do is run or execute or evaluate the function. That's all we can do. So this is what we're going to do. We're going to try and predict what this true function is. But here in advance, we know what this function is. We want to predict, say, the response surface later on. So this is what we're doing. The first part involves collecting the training data. So here, for example, suppose that we are going to evaluate the black box function f of x at 4 points. So we're going to evaluate it at -1.03, 1.76, and so on at these 4 points. So we take these 4 points, we run this function f of x, and then we get 4 outputs. So we get the value for the first point, the value for the second point, and so on and so on. So you see that this X matrix, if you will, the bottom portion is corresponding to the X inputs for the training data. And then here for the Y, the 4 points at the bottom correspond to the 4 Y outputs for the training data. Now, at the top of this X matrix corresponds to 2 prediction points. These 2 points are where we want to perform the prediction. Here on the right, the 2 outputs are not known at the moment. These is what we want to predict. So after you've gone ahead and obtained your training data, you specify your prediction points or your testing points, then you must go ahead and select a covariance function or kernel function. Here I'm using a simplified form of the radial basis function kernel. Here, since we sourced a lot of this material from the book Surrogates, the author describes this simplified RBF or radial basis function kernel as the inverse exponentiated square Euclidean distance. The reason I point this out is so if you want to go back to the book and search for this, you can look for this exact phrase and you'll learn more about this kernel function the author discusses. So after you've selected your kernel function, and I should point out that there are multiple kernel functions. There are the exponential kernel function, there is the Matern family of kernel functions or covariance matrices, RBF or radial basis functions. There are different ones out there, but here I just wanted to point out which one we're using for this example. So once you have your covariance or kernel function, you need to compute this in, well, here I do it in 2 parts. Number 1, I calculate the so-called distance matrix. This is seen as sort of the norm between x and itself, otherwise norm between x and itself, or x and x squared. X here is going to be the combination of the prediction points where we want to perform the prediction, these 2 points, and the training points. So these 4 inputs, if you will. So that's what we mean by X on this slide. Once you calculate the D matrix, you go through each element each element of your distance matrix, and you perform this operation e to the negative d. And so here, if you want to do it by hand, I've done it for you, just so you can follow along. So here, this is the norm between 0.1 and 0.1, the norm between 0.1 and 0.2, the norm between 0.1 and 0.3, and so on and so on. Or rather, this is the distance, not the norm yet. or sorry, it is. There are two things to notice about this matrix. Number one, the diagonals are all 0. So basically the distance between point 1 and point 1 is 0. The distance between point 2 and point 2 is 0, and so on and so on. Another thing, whatever is on one side of the matrix, you can see that it's symmetric. So whatever's on this corner is on the opposite corner of the matrix. Once you calculate the distance matrix, you then plug it in to your E term. So E to the -0, you get 1. E to the -1.429, you get this value. And notice that the term here in the upper right hand corner is basically every term here. So 0.1429 is E to the -1.429. So then you repeat the process again and again. So again, the diagonals here are now all 1. And now the whatever terms are here on one side of the matrix, it's symmetric onto the other side. Sometimes you hear the covariance function referred to as the covariance is referred to as a correlation function. So basically, if you have a point very close to point 1, what's the output going to change? Or rather, I'll hold off on discussing the correlation matrix here. One thing to keep in mind about this big or large covariance matrix is that it's composed of 4 separate covariance matrices. This first one is a covariance matrix between the test points and itself. This next covariance matrix is a covariance matrix between the test points or the prediction point and the training points. Here, this is the covariance between the training points and the prediction points. You'll notice that this is actually the transpose of the top right hand matrix. And then here at the bottom corner, bottom right, this is the covariance between the training point and itself. So once you have all this, you are now ready to use the MVN conditioning equations, sometimes called the Kriging equations. So I'm sure everyone here has taken a course on linear algebra, so you know how to perform these operations here. Here, if you do it by hand, the predicted output at those 2 points is 0.285 and 2.95. Here, when you use the variance equation, you actually get a matrix of quantities. The final variances for your predicted values, here we have 2 predicted values. The variances for these 2 predicted values are the diagonal terms. So the variance for the prediction 1 is 0.11, and the variance for prediction 2 is 0.051. These variances are giving us an idea of the prediction uncertainty. If the prediction uncertainty is very high, that means we cannot trust that prediction so well. If the prediction uncertainty is low, then we have a higher confidence in that predicted value. And keep in mind, these prediction uncertainties should be compared with other predictions to gauge relatively how well the prediction is. So if you want to replicate this example, you could use MATLAB for this, but here I'm using R. Here on this slide is the code that you would use with R. R is a math software package that's used in statistics. So here are the code. If you want to go ahead and replicate this, it's here for you. Note that the output from this code is the same mean values of 2.5 and 2.95 that we've calculated on the previous slide. The variance matrix too, you'll see that these are the same values that we've calculated by hand. Now, here it's the same code, slightly modified because we want to see plots. So here we've gone ahead and updated the code from before to after, and then these are the plots we get. So the first plot is the mean function. This is the predicted response surface. This is the surrogate model. If you want to make a prediction, you plug in your inputs here, you run it, and then you get your predicted values. Here on the right is our standard deviation, or the square root of the variance. So basically this is giving you an idea of the prediction uncertainty. If you're in the white or the yellow region, that means you don't have enough data to trust your predicted value. So for example, I want to make a prediction in this region. The prediction uncertainty will be, or your variance or your standard deviation would be very high. But as you move close to a training point, your prediction uncertainty, your variance, your standard deviation drops. It's low. Ideally, what you want, if you want to believe your predicted output, you want to have a low standard deviation, a low variance, or a low prediction uncertainty. So let's move on. Here on the left is the true function. Here on the right is the predicted function. You can see that we've only used, 4 training inputs. So you can see if you counted 1, 2, 3, 4. And this is the resulting mean function, if you will. This is your surrogate model. You can see that the surrogate model does a decent job of predicting one extrema. Here it's predicting a maximum, but it's not, it completely missed the other extrema, which is the minimum. So here what we can do is move on to the next example. In the second example, we are going to use more training points. In the first example, we used 4 training points. In the second example, we are going to use 40 training points. You're going to find out that at the end, not only do we predict the maximum, we also predict the minimum. And this final surrogate model that you see here, the predicted function, is going to better align with what the true function is. So we can do this by hand, or we can use R. If you want, you could use MATLAB. You can use the code here for R and replicate this example. And here's the output of this Gaussian process regression using the MVN conditioning equations, or the Kriging equations. Here on the left, our mean function. In the circles are each training point. Here in the blue region, this is the minimum. And here in the yellow region, this is the maximum. So this is corresponding to what the true function is. Here on the right, notice that there is more red. Remember, here red means good. Here, the fact that we use more training inputs means that the prediction uncertainty has been reduced in a good part of the design space. So here, everywhere where you make a prediction that's in the red region, that's a good prediction. Anywhere where you're in the yellow region, and notice that we're far from any of the training inputs. That means if you make a prediction here in the yellow region, we don't have enough information to tell whether or not the prediction is good or not. So let me repeat that in another way. If your prediction is close to a training input, that prediction is reliable. If your prediction is far from a training point, that prediction is not as reliable. Now, here's a prediction of the true and the predicted function, if you will. You can see that, again, we have the minimum predicted, but we also have we have the maximum predicted, and we have the minimum also predicted here. So there you have it. That's how you, in a very general sense, how you use Gaussian process regression to produce your surrogate model. Your surrogate model being the mean function. Always remember that whenever you use Gaussian process regression, you get both the mean function and your variance function. The variance function is used to gauge whether or not a prediction is reliable or not. Now, we just went over the first goal, which was fitting the model, constructing via Gaussian process regression your surrogate model. The next part of this presentation is going to be focusing on the acquisition functions. These acquisition functions are going to determine the next design, the next configuration of your FE model that might be a better design. So just a quick note here, these acquisition functions are stemming from what's called Bayesian optimization. Now, Bayesian optimization, there's a lot to it. I could easily go for 2 hours about this, but here I'm just going to give you a quick excerpt from this lecture I found. Feel free to pause the video and have a read through it. The most important part of this entire explanation is the line I've underlined here. So remember, these, or rather Bayesian optimization has yielded these acquisition functions. Now, what is an acquisition function? If I go back here, there are multiple acquisition functions available. There are some for the objective, there are some for the constraints. You can combine these acquisition functions together. Now, I'm going to go through each of these in the next few slides. So the first one is the EY criterion. This is basically the surrogate model, the mean function. So here as an example, let's suppose that you have 1, 2, 3, 4, 5 training points. You perform Gaussian process regression. Now you have the mean function here. This is your predictive function. Now, with the EY criterion, basically we find the minimum here. If our problem was to find the minimum, we take the minimum of the mean function. Here we'll refer to this point as xn plus 1. This is our candidate point to evaluate next. So here we run Nastran, or we run our black box function, which could be an FEA program, CFD, or MBD. We run Nastran at this point. We update the mean function, and we repeat the process again and again. So this is a very simple process. We find the minimum to the mean function, and this is where we run Nastran next. Now, there are more exotic criterion functions out there. The next one is called the expected improvement criterion. I'll go over what each term means and the expression in a moment, but just know two things. Number one, this is a combination of exploitation and exploration. It's exploitation because we are using information from the mean function to guide our decision process. And then we're using exploration because if you recall back, when we supply our training points or training data, we have not sampled the entire design space. There are regions of the design space where we do not know anything about this region. So the second part of this acquisition function is so-called exploration. We're going to be exploring other parts of the design space that we have not explored yet. So again, this is taking information that we know from the mean function, the surrogate model, and it's taking information that from the variance, if you will, the variance function. So let's look at a quick example here in the top right-hand corner. Let's suppose you repeat the process. You have 5 training points. You have generated your mean function in the black line here. You have your variance or your standard deviation that's used to compute what's called the prediction interval here in red dotted lines. You'll notice a few things. Number one, the surrogate model is telling you that there's a minimum here and there's a minimum here. The variance function is telling you that we have a lot of information here because the dotted lines are very narrow, but here the variance is very high because the dotted lines are very large. The prediction interval is very large. So here we're going to take these two into account and produce what's called the EI, or the expected improvement criterion. So here in blue is the EI of X function. We're going to find the maximum here xn plus 1. This maximum is where we are likely to find a better solution, a better minimum to this problem. So here we take xn plus 1, we run Nastran or our black box function. Here we have a new black point. This is the output of the black box function or Nastran. We update the mean function, we repeat Gaussian process regression, we generate the mean function and the variance function, and now we recompute EI of x. And now you'll notice that this previous peak, if you will, is now flat. That means we have a sufficient amount of information here, but here on the right, you can see that EI of x is high. This could be due to the variance term, the second exploration term. This here is telling us that it might be worth exploring this area for a better minimum. So here we take this as xn plus 1, and we run Nastran or our black box function again, and we repeat this process. We run Nastran, we have updated training data, we update the surrogate model, we reevaluate the acquisition function, we solve this problem, find the maximum of the acquisition function, and we repeat the process again and again. So here on the next few slides, I have an explanation of what each of these terms means. Feel free to pause the video and go through these slides. Here, let me go to the next one. I also have links so you can read more about what these different terms mean. And now there's a second acquisition or a third acquisition function I want to go over. This one's called the probability of improvement criterion. So here, you'll notice that this expression here is actually part of the EI criterion, but it's only using information from it's using information from both the variance and the mean function. But here, think of it as only taking into account exploitation. Now, when would you use this exploitation criterion? You can use this when the expected improvement criterion does not yield a good solution. For example, if you're dealing with a problem with 20 variables or parameters, 20 parameters is a very large problem. EI, you're going to be exploring a lot to find a good solution. With 20 parameters, your design space is very large. So here, when EI is going to be taking a very long time, you could switch and use PI. PI can use a faster solution, but the drawback for PI or probability of improvement is that you are not exploring. You're just exploiting what you have right now. So that's when to use PI. If you're dealing with a big problem, say 10 or more parameters, try using PI instead of EI, because EI will be exploring a long time and you won't see a benefit to that. Later on in the FAQ, I go into this in more detail. Now here, how do we handle constraints? So when you have constraints, you're working with what's called the probability of feasibility, or sometimes satisfaction. Here, the abbreviation could be POF. Here, we're assuming that the constraint is of the form C of x is less than or equal to 0. Now, the acquisition function for this is going to be described as follows. Here, we're going to be taking the product of multiple POFs, if you will. Here, this exotic term, if you would think back to sigma is basically a summation. This term is basically the product. So the product of the first probability of feasibility for the constraint 1 multiplied with the probability of feasibility for constraint 2, and so on and so on. So here, this is your probability of feasibility for one constraint. Now, here again, you can pause the video and read through what each of these terms are. Here, let me give you an actual example with responses you might be familiar with. Suppose you have a constraint. Here we have a stress constraint. We are saying that the stress can be between 15,000 psi, pascals, and it could be between negative 15,000 and 20,000 psi or pascals, whatever your units of stress are. What you do with these stress values, you're going to run Nastran multiple times. You're going to have multiple values of the stress, one for each training point. You're going to take all of these stress values that are in your units, psi, megapascals. You're going to normalize these constraints. So you have these constraints expressed in this form. C is less than or equal to 0. So a consequence is that you now have a normalized constraint, or rather a set of normalized constraints for the lower bound, and then you have a second set of normalized constraints for the upper bound. So once you have these normalized responses, if you will, for the lower and the upper bounds, you apply the MVN conditioning equations to produce both your mean function and your variance function, as I have it here. Let's go ahead and see here. Right, so you have your first set of mean and variance functions and your second set of mean and variance. Once you have this, you then plug it into your probability of feasibility expression that you have here. So then you have one term and a second term, and then your final probability of feasibility or satisfaction would just be the product of each term here that you have. So now, that was the probability of feasibility. Now, how do you combine these two to perform a constrained optimization? So you can take the product. You take the product of your objective acquisition function and you take it with the acquisition function of your constraint. So here, if you look here at the bottom, I have my so-called joint acquisition function. Here you can call it the expected feasible improvement function. You basically take the product of EI with a POF, and then you look to maximize this function E of I of X. Wherever the maximum is, this is your next candidate point to evaluate. And then you repeat the process again and again. One quick note. When you're calculating EI of X, when you are using the term F sub M or F min to the N, this term is only taking the values for the feasible designs. When you run Nastran multiple times, some of your designs or your points are going to be feasible, they satisfy the constraints, and then other points are going to be infeasible, where they violate the constraints. When you're using this term F min, if you will, you're only taking into account the valid designs that satisfy your constraints. That's one very important detail to keep in mind. So there you have it, the two goals. We went through Gaussian process regression. We've gone over how to use MVN conditioning equations to construct your mean function and your variance function. The mean function is used to predict the outputs of your FE solver. The variance function is used to gauge the prediction uncertainty of your predictions. The second thing we went over are the acquisition functions. How are the acquisition functions used to pick your next candidate point? Ultimately, you take both of these things and you combine them into this algorithm. Step 1, you generate the training data. You run Nastran at different configurations of your FE model. You collect all the outputs. Here we'll refer to the outputs as YN. You'll then use these to construct your model, your surrogate model using Gaussian process regression. You use these surrogate models to construct your acquisition functions. Your acquisition functions are used to pick the next candidate point. You then run Nastran. You then update your model again, and you repeat the process again and again until you're satisfied with the improvement in the design. Now, here, if you're watching this presentation, you're aware that the Nastran Solution 200 web app has a capability to perform machine learning with Nastran. In the next few slides, I'll go over some of the settings that you can configure. Here, I just went over this diagram in one of the previous slides. Here, you can control the following. You can control the number of iterations, the number of loops you go through. So say if you want to run Nastran 100 times, you can specify this with the number of iterations setting. Now for the acquisition function, remember that you can switch between the expected improvement and the probability of improvement acquisition function. You can control this with the acquisition function objective setting. Here is basically a repetition of what I just said. If you're using the machine learning web app, if you go to the settings section, you select machine learning, you can specify the number of iterations, and you can specify the acquisition function, either the EI or the PI criterion. And here is just a repetition of this. One quick comment regarding the acquisition function. So suppose, or rather, when I have tested the expected improvement criterion, it works well if you're dealing with 1 through 5 parameters or variables. It also works well in some cases if you work with 10 parameters. When you are working with, say, 15 or 20 parameters, expected improvement does work, but you're going to run Nastran or your black box function multiple times. Remember, with 20 parameters, your design space is going to be very large. With expected improvement, you're going to be exploring a lot. So expected improvement may not yield a quick enough solution to you. An alternative to expected improvement for large problems, say with 20, 15 parameters, is to use what's called the probability of improvement acquisition function. And here in this example, I believe I was working with 16 parameters at the time. You can see with PI, during the machine learning portion of the whole process, you can see that it's actually finding a solution faster than EI. So again, if you're dealing with 10 or more parameters, EI may not yield a solution quick enough because you're exploring a lot. An alternative to that, a compromise, would be using probability of improvement. One thing you can do is you can use EI at the beginning just to do some exploration, and then after a few runs switch over to probability of improvement to polish that previous best solution. After that, you can then switch over to a gradient-based optimizer to further improve that design. Now, there are a few more things I want to say here. To find precisely the minimum or the maximum will take a lot of function evaluations. What you get with these acquisition functions, you get an approximation of where the minimum or the maximum will be. So this is what I mean by, after your machine learning process, switch over to a gradient-based optimizer to finalize and polish the best design found so far. Now, just a quick conclusion. Remember that machine learning, there are a lot of concepts out there for machine learning. In this presentation, we only focused on 2. We focused on Gaussian process regression to construct our surrogate model, and we focused on Bayesian optimization to help us pick the next candidate point, the next potentially good FE model configuration. Ultimately, we take our knowledge of the Gaussian process regression and the acquisition functions, and we can implement an algorithm here to construct machine learning. Now, a quick FAQ here. So these are some questions I might get asked when you're watching this presentation. The first question might be, when do I use the methods I described in this presentation? So let's go ahead and go over that. Here on the left is when you would use your gradient-based optimizer. If you have a linear response, such as the one found in Solution 101, statics, Solution 103, normal modes, and so on and so on, if you have a linear response, and if you can supply the gradients, then you can use a gradient-based optimizer. Here, obviously, you would use Solution 200 to perform an optimization. This works really well if you're dealing with 1, 2, all the way to thousands of variables. So I recommend always try to use Solution 200 when possible. When do you use Bayesian optimization? So basically, when do you use these acquisition functions? When do you use machine learning? Here, you would use machine learning when your gradients are difficult to calculate or they are not available. One prime example of this would be when you're dealing with nonlinear responses, such as those found in Solution 400 or Solution 700. I have personally tested this on Solution 400 responses, and it has worked well. Another reason to use it, machine learning, is when your solver runs are very time consuming. Maybe you might spend a few hours, maybe a few days. Machine learning is one potential solution to this. One other critical thing, the number of parameters. When I was going through some of the papers available for Bayesian optimization, most papers were dealing with problems with 1 through 5 parameters. It was very rare that I found a problem dealing with 10 or more parameters. In another paper, I found out that the author claimed that this worked well between 1 and 20 parameters. The reason is because as the number of problems increases, your design space becomes larger and larger. So you're going to have to learn more, explore more to find a solution. So here, use this machine learning technology when you have a small number of problems, 1 through 20. Personally, I have tested this between 1 and 16. I'm sure I could, if I had a problem with 20 parameters, it would work well. I'm sure that if I tested this with 30 parameters, the number of function runs would be too much than what's practical. Another question, how many runs to use for the training data? Right, so your whole entire process will consist of 2 phases. Phase A will be used to acquire your training data, and phase B will be used to this is your machine learning phase, if you will. So your training data, you're going to configure your FE model for different configurations. Say here in this example, we have 100 configurations of the FE model. You're going to run Nastran for each configuration. So you're going to run Nastran 100 times. In the second phase, your machine learning phase, here we run, it looks about 160, maybe 160 iterations here. 160 Nastran runs for the machine learning phase. So for the training data phase, this is what's used to construct the initial surrogate model at the start of the machine learning process. So here is the start of the machine learning process is the dotted line. To start, you need a surrogate model. And the training data phase is what's used to generate that training data. So now, how many runs per parameter should you use? Personally, when I've tested this with a few problems from 1 through 16 parameters, I have found good results with 5 runs per parameter. So here, as an example, let's suppose you're dealing with 10 parameters. You would run 10 times, or 5 times 10 would give you 50 runs. So you could run Nastran 50 times, 5 runs per parameter for your training data, and that would be a good start for your machine learning process. Now, this is a big contrast with prediction analysis, if you will. Gaussian process regression can be used to construct the surrogate model. The surrogate model can be used to perform predictions. That requires more runs. So for example, if you have 5 parameters and you wanted to perform a prediction manually, you would need to run it 10 runs per parameter. If you're dealing with, say, 10 or 15 parameters, you would need to maybe run 20 runs per parameter. That's if you're just predicting. If you're just predicting, you are not using machine learning. You're not using Bayesian optimization. But if you're using Bayesian optimization, you can start with 5 runs per parameter. Now, another question you might have, you might be dealing with 15 or 20 parameters. You might be running machine learning, and you might get this. You might get a flat line after 100 runs. You might be asking, why is it flat? Why don't I find another better solution? The answer is because your design space is very large. 15 or 20 parameters, you're going to be exploring a lot. So this is what I recommend to handle this scenario. When you run this machine learning exercise, use the EI criterion first, so your algorithm can explore a little bit. After a few runs, then switch over to the probability of improvement criterion, because that will just be doing pure exploitation. You'll notice that when you run machine learning, as long as you get a drop in your best valid design, that indicates that you are successfully optimizing. It's okay to have these flat regions, but if your flat region is prolonged, then that's when you have to use a combination of EI and PI. After every machine learning optimization, if you will, I recommend, if possible, running a gradient-based optimization. This is so you take the best design so far and you further improve it with the gradients of your optimization. And one last thing I want to leave you off with, I know when I first started doing optimization, I was always focused on finding the maximum or the minimum to my objective. And when you're doing production work, that may not always be a practical thing to do. It might take you months to find where the minimum or the maximum is. So here, my definition of optimization has changed. As long as you are improving the design every hour, every day, the last best design is your optimal solution. So here in this example, after 16 runs, I have successfully reduced the objective of this function. I have found a better design. So this, I am achieving optimization. But after that, I no longer achieve optimization. There's no change in my objective. So here, I would say that my optimal solution is at run 16. But after that, there's no solution. So I would stop there. That's my solution. And then I would continue on from there. Now, one thing I forgot to leave you off with is my contact information. So here, I'll just go ahead and leave it for you. If you have a question with any of the topics in this presentation as it relates to machine learning and Nastran specifically, please contact me at this email address. I can guide you on the tools you can use. I should also mention that Python, there are a lot of Python libraries available if you want to perform this optimization. If you need someone to help steer you on selecting a Python library, you can reach out to me. If you want to use the Nastran web app for machine learning, you can also reach out to me and I can work with you on giving you access. And then you have a specific question on machine learning with Nastran, you can also contact me. With that, thank you so much for watching.